Okay, so we were looking at bisimulation and CTL in the last class, right? So what did we say? That if there are two processes or two Kripke structures which are CTL equivalent in the sense they satisfy the same set of CTL formula, then they are bisimilar, and the other way around also it holds. So if they are bisimilar, then they also satisfy the same set of CTL formulas, right? And you can also extend this to CTL star. And in fact, we had this game characterization. And we mentioned that if you look at the game, then by by looking at the movements or the actions that the challenger takes, you can actually find a distinguishing formula if the challenger wins, right? And then we also said that like there may be some finite number of steps in which the challenger should win if the challenger wins. And then in fact like you can get formulas, distinguishing formulas which use atomic propositions, conjunction, negation, and existential this operator, right? Like the path operator, there exists a path, this operator. And uh, yeah, so you can just use these ones to in fact find a distinguishing formula. So in fact, if the two Kripke structures are bisimilar, you can have a more tighter result. I mean, which says that they should agree only on this set of formulas. That should suffice. Okay, this set of operators, formulas with this set of operators. Okay. Now, yeah, we also said like so. This thing is this equivalence holds for image finite Kripke structure. So, what is an image finite Kripke structure? Like so, you can have essentially from any particular state, it has finitely many successors, right? So that's and then we moved on to talking about binary decision diagrams. So binary decision diagrams are essentially data structures. So these are data structures which represent Boolean functions. So you can have different kinds of normal forms like conjunctive normal form, disjunctive normal form. So we looked at this if then else normal form, right? And it used this thing called the Shannon expansion, and you had a set of variables in the Boolean function, and these variables are ordered in some way. And what we also mentioned is like if sorry, for a given Boolean function, if you order the variable in a specific way, if you have the variables in a specific order, then what do you call then this the BDD that you have, the binary decision diagram, this is unique for every function, right? And we can prove this using an induction on the number of variables. So how does a BDD look like? I mean, essentially, like if you recall, so you have the if then else normal form is like this. If X is true, then this is we call it the high branch, the first one, and then this is the corresponding to the false, this is the low branch. Okay. And we looked at like these different examples of Boolean functions and how you represent them using BDDs. Okay. And um, yeah, so the way we construct a binary decision diagram is like you can consider such a decision tree, and then you can merge the nodes which are common. They have like the same high and the low, all the zeros and the ones, the terminal nodes. First, you can consider them just as one node for zero, one node for one. Then you can also consider the nodes, for example, here, this thing you see y201, y201. So these are the same nodes. You can just consider one of them. And this gives you a DAG. So that is essentially the BDD, the binary decision diagram. And we also talked about an ordered BDD. What is an ordered BDD? Like along all the paths, the sequence of variables that you are checking, it should be the same along all the paths. So that is an ordered BDD. And reduced order BDD or ROBDD is essentially one where you have like there should not be any duplication, and if you have like you should not have any kind of test which is not useful, like both the high branch and the low branch they are going to the same node, then you can remove that particular node. So if there is a node u and that's going to another node v, let's say on both the high and the low branches, then you can remove the node u. Okay. And essentially, you can again, if you have two nodes, let's say U and V, such that they are high, low, and their labels, like by label, I mean the variable that you are testing, they are the same, then the two nodes U and V are the same. So that is the idea of this reduced order BDDs. And often when people say BDD, they essentially mean ROBDDs. Okay, so that's the kind of terminology. Now, yeah, so we pretty much did all these things, and then we said this canonicity lemma. So if you fix the order, then exactly one ROBDD representing a Boolean function, right? And we sort of discussed the proof overall. Okay, so now there is one thing which I'd like to talk about, which is just recall the definition of bisimulation. So in bisimulation, what we have is like we have this, it's a relation, it's a binary relation over states of Kripke structures, right? And how is this defined? So you say that S1 and S2, they are related if their labels are the same, and for all successors of S1, if you consider a successor S1 prime of S1, then there should exist a successor S2 prime of S2 such that S1 prime and S2 prime are related, and vice versa, like in the sense that for all successors of S2, there should also exist a successor of S1 such that they are related, right? Now, I can try to see there can be some other similar relations also. So for example, I can talk about a relation which is a one-way thing. Like you say that for all S1 prime, which is there in the, which is a successor of S1, you can consider a successor S2 prime of S2 such that S1 prime and S2 prime are related. But I'm not talking about the other direction, like for all S2 prime, right? So it's called a simulation relation. So S1 and S2 are related. So why it's a simulation? In the sense that whatever S1 can do, S2 can also do that, right? So in that way, you say that S2 simulates S1, but it may not be the other way around, right? Now, when you have the simulation thing, you can also immediately see that in terms of the trace equivalence, or in terms of the traces, what is the kind of relation that you would get if I talk about the traces? The trace of S1 is a subset of trace of S2. It may be possible that S2 can do something more which S1 may not be able to do, right? So this just says that whatever S1 can do, S2 should be able to mimic that move. Maybe S2 can do something more also, right? Which we are not talking about here. So this is the notion of the trace. I mean, this is called a simulation relation, and you see it may not be an equivalence because as we are saying that S2 can do more. So it's more like, so this is like, what are the things you can expect here? What kind of properties? So it is reflexive, right? Because if you consider S1, then whatever S1 can do, this S1 can also do the same thing. It's reflex. It's also transitive, right? This relation is also transitive in the sense that if S1, S2 can simulate S1 and S3 can simulate S2, then S3 can simulate S1, right? If S1 can be simulated by S2, S2 can be simulated by S3, then S1 can also be simulated by S3. So it's transitive, right? So what do we call it? A relation that is reflexive and transitive. It's a pre-order or a quasi-order, right? It's a pre-order. So it's already written here, simulation pre-order. So we have this simulation pre-order, right? And you can also consider an equivalence relation out of this, okay? Now, what is the equivalence relation? So I say that S1 and S2 are simulation equivalent, right? So I will say this is like S1, S2 is like S1 can be simulated by S2. S1 and S2 are simulation equivalent if S1 simulates S2 and S2 simulates S1. Okay. So now you see that this is again an equivalence relation. If S1 simulates, so this is a reflexive relation. This is a symmetric relation. If S1, S2, S1 simulates S2, then S2 also simulates S1, symmetric relation. Also, it's a transitive relation. So this is also an equivalence relation. But the thing is that what one should note is that this is not exactly the same as the bisimulation relation. So I'm not saying that at every step it's like that vice versa thing. I'm saying that this is just your simulation preorder. S1 is simulated by S2, and you say S2 is simulated by S1. If these two things happen together, right, then I call it a simulation equivalence relation. Okay, so is it clear that why it is not a bisimulation relation?
But if S1 can simulate S2, then that means for every successor of S2, there is a successor of S1,
Yes.
and vice versa.
No, the vice versa I'm not saying. What I'm saying,
But you said S1 simulates S2 and S2 simulates.
S1 simulates S2. So what is the thing like S1 simulates S2? So, okay, so let's think of the game. So there is a challenger and a defender. Can you tell me, like, just think of the simulation pre-order? Okay. So how will the game look like in the case of simulation pre-order? The simulation pre-order game, how will the, so you have S1, you have S2. There is a challenger, there is a challenger player, there is a defender player, right? So how will the game look like now?
Challenger will keep picking some path along S1.
Challenger will keep picking some path along S1.
Give the corresponding path.
And the defender will try to mimic that, right? And now,
here you can't switch.
Here you can't switch.
Okay.
Right? Now, if I ask you, so is it now it's clear that like you cannot switch, right? See, so sometimes when you think of this as a game, it becomes slightly clearer. You get a different perspective, you get to understand things in a different way, right? So indeed, like if you think of this as a game, you see that there is indeed a difference. Like just by looking at the definition, it's not very obvious, but if you think of this as a game, then indeed there is a difference you can see between the bisimulation and simulation equivalence, right? So in simulation equivalence, what is happening? Like you are, these are the two things. You start from here, you play, and then the other guy is moving. In the other case, S2 simulates, that is S2 simulates S1. When you say S1 simulates S2, you start the game, challenger will start from S2 play, and then S1 defender has to move. So the swapping in the middle is not allowed to happen, right? Now, if I talk about, suppose S1 and S2, they are bisimilar, okay? Uh, is it the case that they are simulation equivalent and vice versa? So we have talked about so far three kinds of equivalence relations, right? So what are the three equivalence relations? Can you tell me? Sorry? Trace equivalence. Trace equivalence. Then bisimulation equivalence or bisimilarity. Yeah, okay. And then simulation equivalence, right? So, Rishal, are you able to follow me?
Yeah, makes sense.
Okay. So there are these three types of equivalence relations, right? So now we have already talked about this trace equivalent, like if they are bisimilar, two states are related by the bisimulation, by a bisimilarity relation, then they are also trace equivalent, right? What about these two?
It's also simulation equivalent.
Sorry?
If two structures are bisimilar, then they're also simulation equivalent.
That's what you think. If two structures are by simulation equivalent, then they're simulation equivalent. Okay, so what is the intuition?
Because they correspond to a weaker class of games without changing sets.
Right? So, for example, like if they are bisimilar, then you see that the challenger is even more powerful and the defender is able to mimic the move of the challenger. Right? The challenger can switch and the defender is able to mimic. So, if the defender can win against a more powerful challenger, then the defender can also win against a less powerful challenger. Correct? So if they are by simulation equivalent, which means the defender wins against a more powerful challenger, then they are also simulation equivalent. The defender can win against a less powerful challenger. Clear? What about the other way around? If they're simulation equivalent, are they going to be by simulation equivalent?
Not.
Not seems like may not be, right? So now then what should be the next thing that you should think of? Sorry?
You want to give an example?
You want to give an example of what?
Something that is simulation equivalent but not by.
Something that is simulation equivalent, but not by simulation equivalent, right? So this can be a good exam question. I mean, if you have to think it in the exam, it may be difficult. But if you think after, I mean, a little bit in advance, you might be able to find out. Okay, it's not that difficult. But like if you're doing it for the first time, it might take a long time. Okay. So there are other kinds of things also one can think about. So for example, like, so I talked about this bisimilarity relation, right? Which is the largest bisimulation relation. So you can, so if I give you two structures, or if I just give you one Kripke structure, the set of states and all, right? A Kripke structure has set of states. So how do you compute the bisimilarity relation, right? So there has been, I mean, I think there has been enough research on just how you can compute these relations, like what is a good algorithm, what is an efficient algorithm. So if I just give you a Kripke structure, you can get something, I think, which is of the order n square or e square, something which is not too difficult, but one can also get something which is, I don't exactly recall, but I think something like of the order n log m or n log n, something like this. So this is a more difficult algorithm, but you can try to think of something which can give you something like order m square kind of a thing, or this may be order m log m. I don't exactly recall like what is this thing, but something of this kind, which is order m square or order n square. That's not too difficult an algorithm to compute the bisimilarity relation, right? So, this efficient algorithm was given by Tarjan. If you've heard of like, so Tarjan was again another Turing award winner uh, who predominantly worked on different kinds of algorithms. And he also had an algorithm for computing bisimilarity relation to give fast one, essentially. Okay, so these are things you can think of, like, so how to compute a bisimilarity relation just from scratch. Like, I mean, if I'm giving you just a Kripke structure or two Kripke structures, let's say, but to keep it simple, just one Kripke structure, you want to compute the bisimilarity relation, which is the largest bisimulation relation, right? How do you compute them? How do you find, uh, say, two Kripke structures uh, that are simulation equivalent but not bisimilar? Can you find such examples, right? And these are things, if you try out yourself, then you will find that like the relations will become much clearer to you.
So the previous example we gave earlier, that is not by simulation equivalent.
Uh,
The uh,
so we had seen such an example,
what I think is
such an example, right?
so if we can show that if we give if the challenger is in K2 and the defender is in K1, this will
Uh, So are this simulation? So K1 can't, so these are also not simulation equivalent.
Alright.
These are also not simulation equivalent, right? Because K2 cannot simulate K1 and they are not bisimilar either. If they are not simulation equivalent, they are not going to be bisimilar. Okay. Yeah. If they're not simulation equivalent, they cannot be bisimilar. But the question is that can there be some Kripke structures? The answer is yes. You can find something where you will have to find like yeah, two Kripke structures which are bisimilar. Sorry, which are simulation equivalent, but they are not bisimilar. Okay. So yeah. Okay, good. So okay, so the definition is clear now. Then simulation pre-ordered, simulation equivalence, bisimulation equivalence. So these are different, uh, like trace equivalence, bisimulation equivalence, simulation equivalence. These are different relations. What about the thing between trace equivalence and simulation equivalence? Like which one is stronger? If two things are simulation equivalent, are they going to be also trace equivalent? They will also be trace equivalent, right? So in fact, like the strongest one is this one by simulation. So this is one, this is two, this is three, right? From stronger to weaker. Okay, right. Uh, yeah. Okay, good. So we were talking about symbolic model checking. So this is slightly more now this the BDDs and all that we are going to talk about. This is more applied, like in the sense that people actually use them when they do formal verification on some code and hardware and things like that. So what is the notion of explicit model checking when you do with respect to every state, right? Like we say that, oh, you have this particular state, initial state, you want to compute whether it satisfies a given CTL formula phi. So you compute for every sub formula. If you recall that we talked about these, the parse tree and the sub formulas, and then we say like for every sub formula, you find the set of states that would satisfy the sub formulas. So if you are doing this individually for every state, that is called an explicit model checking. And whereas the idea of symbolic model checking is one where you do things with sets of states, right? I mean, the sets of states can be represented using a formula and which captures these sets of states. So we'll just see how, I mean, a formula can capture such states. So essentially, you can encode the states using bit vectors. Okay, you can encode the states using bit vectors. So you have these states, and then you can have such an encoding, right? So for example, if you have four states here, you can say that you will need two states, sorry, two bits, and the encoding is like this. That S1 is encoded with 00, S2 as 01, S3 as 10, S4 as 1, so on, right? And now you can define what is called a characteristic function, which is essentially like if there is this the characteristic function, it defines a set of states. So if there is a state S which is in that set, let's say capital T, my capital T is the set of T is a subset of S. Okay. So if my if S belongs to capital T, then what happens is that this characteristic function, when it takes the argument S, it gives 1 if S belongs to T, otherwise it's 0. Okay. So let's see. Yeah, maybe we can try to see, for example, let's say if I have just let's say S1, S2, these two sets, these two states. Okay, so you have like 0, 0, okay, and you have 0, 1, right? So what you can say, you can consider two variables like corresponding to these two bits, x1, x2, and this is more like negation of x1, negation of x2, right? And you can say that there is a conjunction between the two, negation of x1 and negation of x2, and you have negation of x1 and x2, and here you can say that these two, it's like a disjunction. So you have this state, or like, so this state is given by this particular function, this state is given by this function, and when we are talking about the union of these two states, like, I mean, essentially you have so many sets, it's more like you can say that there is a disjunction between uh, them. Okay, and this is essentially the function which is the same as just negation of x1. Okay, so this negation of x1, hence it denotes the set s1 s2. That's the idea. And similarly, you can also do for the for the uh, transition relation as well. Okay, so here what would you do? Like, you have a function delta. Okay, so again we are going to define a function, a Boolean function. But now we are going to use 2n bits. Why 2n bits? Because this will be like the first n bits may correspond to a source state. The second n bits may correspond to a target state. Okay, so you have 2n bits, and so yeah, right. So you have this n bits for this one, n bits for this one. And so the way I would write this is like, I can have, for example, some x bar, which is a state S, which is the source, and I will use a primed variable here just to distinguish between the source and the target. So this is the target. Let's say it's called T. Okay. And now it's what I will have is like uh, so I'll just write it in this way. I think it will become clear when I, if, so if you have a transition from S to T, then I'm going to say that I have this, like, T will also have some n bits, right? But I'm going to use just the primed variable to say that this is like the target of the transition, right? So you have n bits and n bits. So I'm just going to between to in order to distinguish between like my variables, like so I just use the primed variables essentially to say that this correspond to the target. That's all. Okay. So if otherwise it's like 0. So essentially, if you so the delta, it denotes, like, again it's like a set, right? But instead of having this for a set of states, now we are talking about a set of transitions. Okay, so if there is this transition that is there, then the delta corresponding to this s comma t, it will be 1. Okay, otherwise it's a 0. So just let's try to understand here. For example, if you consider such a Kripke structure, okay, I mean the labels here don't really matter in the Kripke structure. The set of atomic propositions there that are there, that doesn't really matter. But suppose here there are two states, right? How many bits do I need to encode? Just one bit. Okay. So suppose I say that my S0 is given by x equal to 0, and S1 is given by x equal to 1, right? Just one bit suffices. And what are the transitions that I have? They are of the form x equal to 0, then x prime equal to 0, the source and the target. What does it denote? It denotes self loop, right? X is 0, x prime is 0. Then I have x equal to 0, x prime equal to 1, and then I have x equal to 1 and x prime equal to 0, right? So uh, these are the transitions. Now, what can be the function that I can use for this? So this, you see, it's like negation of x. So this is like for each of them. So this one, for example, is negation x and negation x prime, right? This one is negation x and x prime, right? So if I consider now the disjunction of these two, I get a negation of x. And I also have for this, I have uh, x negation of x prime. This is the thing, right? So can you simplify this further? So I put a disjunction here. So what does it boil down to? Sorry,
Negation x or x negation x
negation x
or
or
x and negation.
that is true. That is how it is. But can you simplify it further?
Or negation x prime.
Or negation x prime. This is what you said, right? I mean, is it clear? Because see, if x is true, then if x is false, then of course this becomes true, right? You have this. But if x is true, then you have essentially the negation of x prime, right? So you just have, depending on whether x is true or x is false, you can just simply have this thing, right? So this is is it okay? Right? So the set of transitions you can define using this function. Clear? Good. So sometimes these functions, they are also often called in the literature, they are also called switching functions. They are also called switching functions because Boolean variables, or you can think of them in terms of like they're like switches, like you have on and off. So these functions are also called switching functions. Okay, in the I mean often use this term. Okay, so now once you have this function, then we can do more. What can we do? We can even compute, given a particular state, what is the set of successors for this state, right? We can try to get uh, essentially like a function which corresponds to the set of successors for a given state, let's say. Okay, so yeah, so okay, so the successor state is post of S is like the set of S prime, such that from S you can go to some S prime, and it can be obtained from this delta, right? So this is my delta is this. Do I define? Yeah. So my delta is essentially like this here. Okay. So now I'm saying that if I set my S here, so this is how the delta looks like, right? Now I'm saying that suppose I want to compute the post of S0, right? So I will replace the x with the value of S0. Is it clear? Okay. So if I replace the value of uh, this x with the specific value of S0. So what I'm saying is that, so I'll say delta, or maybe I can say that the function corresponding to this post of S. So this will be like delta, where I put the specific value of S corresponding to X. So this is how I represent this. And then I'm going to get something in terms of X prime. That is the target. But now I will just replace the X prime with also X to get the final set of states, right? I don't want to use X prime, but I want to use X finally. So I'll just replace all the X prime with X. So, and delta S essentially it stands for delta, where x1 equal to b1, x2 equal to b2, xn equal to bn, where again the state S is encoded encoding of S is B1, B2, Bn. Is it clear? Okay. So now, so let's see how this post of S0 is, yeah, post of S0, let's try to compute it. So what do you have? Like now delta of x equal to 0. Okay, so if I have delta of x equal to 0 and then followed by x bar prime should be renamed to x bar. Right? Now what is this thing? This is like negation of x or negation of x prime, where you put x equal to 0. Why x equal to 0? Because I'm talking about post of S0. S0 has x equal to 0. That is the value, right? So I'm just replacing here. I'm x equal to I'm I'm sort of instantiating x with 0. And then in that expression, whatever we get, I replace the x primes with x. Okay. So here I just have a single variable x. So it's like this. So now this itself, like if I look at this part, if I make x equal to 0 here, I already get 1, right? So I don't have anything which is an x prime. So there is nothing to replace. So this is what I get, which is 1. So the function, so this is a function for the set of successors of S0. And what does 1 denote?
Can be anything.
Can be anything, everything, right? The set of every set of states. Every set of 1 is like true. The set of all states satisfy the function 1, right? So 1 corresponds to, right? Like, so this is the characteristic function. So 1 is the characteristic function of the set of all states, right? Character of the set of all states, which is S0, S1. Is it clear? So this is the set that you get. Okay. Uh, Now we can also do it similarly for post of S1. Okay, so what is S1? S1, we had x equal to 1, right? So I have this function, delta was like this. So post of x1, I put post of S1, I put x equal to 1 here. So then I get negation of x prime, right? So this is 0 or negation of x prime is just negation of x prime. And then you make all the x prime you rename to x. So what you get is negation of x. So what is negation of x? It is the set which will satisfy the negation of x, the corresponding, this is the characteristic function. And the set is essentially S0. Clear? So we get S0. So post of S1 is indeed S0, right? So this is how we can also compute the pre for S0 and S1. Okay, so how would you compute the pre now? You set the x prime, okay, and then you set the x prime and then you get in terms of the x. I mean, you don't need to do any renaming further. So you have negation of x or negation of x prime. You set the x prime equal to 0 and what do you get? 1. Pre of S1, negation of x and negation of x prime, set x prime to 1. And what do you get here? Negation of x, right? So this is like the set corresponds to x equal to 0, and that is S0, right? Pre of S1 is S1. Okay? So you can also compute the P. In fact, we'll see that the P sometimes becomes quite useful when we are doing the CTL model checking, like the symbolic CTL model checking. The P becomes useful because, like, if you recall that all these sets we were computing in CTL, right? For example, you can say that there exists a path eventually B, some eventually, let's say, P, something like this. Okay. So how do you compute such a set, like from which there exists a path such that eventually you get to P? So you will first, do you recall like how we computed this thing, this uh, so when we had to do the model checking, we computed the set of states which will satisfy this particular formula, right? How did we do that?
We first take the sets that satisfy P and then we can.
Then you give exactly, right? This is what you uh, did, right? Now, in order to do that, like I will say that you keep going, is essentially like you are computing the pre in some sense, right? The pre, right? And for that, we may actually need to do this, right? So essentially, now you get the idea that you have the Boolean function. So this is the symbolic way of doing this, that you don't do it for every state individually, like from this state, what is the, there is a pre or not. You just consider the Boolean function. And for the Boolean function, you compute the pre. The Boolean function will capture all the set of all the states which will satisfy that property, right? Like where, for example, P holds true, and then you compute the pre. You compute the pre until you reach a fixed point. Okay. So in this case, was it a least fixed point or a greatest fixed point? Is it a least fixed point or a greatest fixed point in this case?
Least fixed point is
Least fixed point. Because you are starting from something and you are growing the function. Okay, so it's a least fixed point. If you start from like a big thing and you remove things, then it is a greatest fixed point. Okay, so now I also told you sometime earlier in the class that how you compute the bisimilarity relation, right? So you should think of this as like you can also think of this as you are computing a fixed point in some way, right? And you should try to think whether you are computing a greatest fixed point or a least fixed point. Okay, so it's similar. Uh, so you have done, for example, this DFA minimization, right? DFA minimization. So there also you kind of find out states which are equivalent to each other, and then you merge those states, right? So here also the idea is the same. And you should try to see that like at some point of time, this iterative computation sort of stops, right? And what I'm saying is that there you should try to think that when you are computing the bisimulation, are you computing uh, computing, for example, a greatest fixed point or a least fixed point. Okay. So these are based on these algebraic structures called lattices. Okay. So you essentially have like there is a partial order on a set. So you have different elements in that partial order. And then when you apply an operator, you go from one element of that lattice to another element. Okay. So if you are at the top of that, like you can say top is something which is, which is greater than. So for example, like if I consider, let's say a set, uh, a finite set, 1, 2, 3, 3. Okay. Now I can have, and then there is a subset relation. Okay. So I can say that my 1, 2, 3 is at the top. Okay. And bottom, at the bottom thing is like the empty set. Now, this is on the elements of the lattice are essentially all subsets of this 1, 2, 3. It's on the power set of this set, right? If A is equal to this, so you can have a partial order which is on the power set of S, and then your subset relation you are considering as the order. Yeah, it's partial order because you can have here 1, 2, then 2, 3, then you can have 1, 3, and so on. Here you can have 1, 2, and 3, right? So you can have essentially the relations will be like this: 1, 2 is here, 2, 3, and then you can have 1, 3, and then everything. So this is the top element, in the sense that for every element in the domain, this is below this using the subset relation. Okay, and this is the bottom element. Right now, suppose you apply some function. Okay, you apply a function. What kind of function? So suppose you say I have a function which may be a union, like t equal to t union 1 2, something like this, where t is some element in this lattice. So this is a lattice. Okay, so uh, so this is essentially lattice. So that there is a formal definition of lattice. I mean, essentially, so it says that you consider any subsets of elements, like maybe these any subset of elements, then you can do something called a meet or a join. I mean, so a join is like you can go up, right? And if you find an element for every subset, if you find an element, like, so since here we are talking about this relation, like, which is a subset relation. So if there is a set which is a superset of all the sets you are starting with, right? I mean, it's like a join of some x, where x is a subset of s. So the join is essentially the union. You can think of this as a union, okay? And the meet of x is like it's an intersection of all these elements. So the join and the meet for every subset should also be in the domain. Then you call it a lattice. Okay. If you have only join or only meet, you can talk about, then it's a semi-lattice and things like that. So there is a whole theory on the lattices, okay, which talks about when you can, I mean, in the lattice, when you apply an operator, and the operator needs to be also, there is this operator also needs to be a monotone operator. So what is an operator? For example, here I'm saying that you are taking the union with some set. So this is an operator. Like, given a set, you take the union with this set. So this is my operator. Operator is taking the union with some 1 2. Okay. Now if I start from here, from the bottom element, then I will go and, like, I apply this on the bottom element, phi union 1 2. I reach here. Okay. So this is a least fixed point, because I start from the bottom element, I reach here. If I start from the top element, 1 2 3 union 1 2, I stay here. This is also a fixed point. So one fixed point is this another fixed point is this here, right? So this is my least fixed point. This is my greatest fixed point. Is it clear? Right? So similarly, whenever you are doing something, like, you can think of like this iterative operators, and you are stopping somewhere, then it's like you are stopping either at a, like, you are stopping somewhere means like you have reached a fixed point. The question is that, like, whether you have reached a least fixed point or a greatest fixed point. In certain cases, least fixed points are more interesting. In certain cases, greatest fixed points are more interesting. Okay, so there can be different solutions. Many things, like if you say t equal to t union 1 2 1 2, 1 2 itself is also a solution for what is a fixed point. Like, if you just uh, I mean, put the solution here, then it satisfies this equation, right? So essentially, like, if you have a function, monotone function f, then you say x equal to fx. So this is the definition of a fixed point. X is a fixed point if x equal to fx. By applying f on x does not change the value of x, right? So that is a fixed point. Now there can be some fixed points which are the least fixed. I mean, there can be many fixed points in general. Some may be least fixed point, something may be the greatest fixed point. Okay, I mean, there can be a least fixed point, there can be a greatest fixed point, and depending on the context, you will find which one is more interesting. Okay, so what I'm saying is that when we are talking about this bisimulation and all, so I do this in more detail in the Automata computability course, but like what I'm saying, you should try to think which one is more interesting. Is the least fixed point more interesting for bisimulation, or the greatest fixed point is more interesting for bisimulation, right? And similarly, we also did this for the, if you recall, for strong until, weak until, we had those equations, if you recall, right, for the until formulas. And then we say that this is the least such set which satisfies this equation. It's the greatest such set satisfying this equation, so on, right? So sometimes the greatest solution, sometimes the least solution, they are more interesting. I mean, okay, so yeah, I mean, in the case of bisimulation, you can think of which one is more interesting, and are we trying to get the least solution, or are we trying to get the or greatest fixed point or the least fixed? Okay, so now, right, so yeah, so we did the pre. So now suppose exactly this is what I was talking about. Suppose you have a pre-star of B, right? It's like there exists a path such that eventually B. Okay. So so initially F0 is XB that characterizes the set T0 equal to B. I mean B is like a proposition, let's say, something like this. Okay. So now if I have to compute this pre-star of B, then I'm computing at every step, I'm computing that fj plus 1, which is the characteristic function corresponding to the set tj plus 1, right? So what is tj plus 1? Can you say? How do I define tj plus 1? Um, just try to remove this.
It will be like TJ union A
Yes.
of
Okay. So what is that? tj equal tj union?
A of TJ.
Yeah, P of tj. So P of tj is essentially like the way is such that there exists some s prime such that, yeah, we have s prime belongs to post of s and what? So these are the set of states such that there exists some s prime that is belongs to post of s and s prime, you are right, post of s and s prime belongs to tj, right? So this is, so now if I talk about the union, sorry, if I talk about the union, in the case of the Boolean function, this will be like a disjunction will come. Okay, the rest is pretty much the same. So I will have fj x bar or exists some x bar prime. There should be some, I mean, the existence of x bar prime essentially says that this x bar prime should not be empty, like, right? I mean, there should exist such a successor and such that delta of x bar prime and fg of x bar prime. Is it clear? This is what fj plus 1. We are just computing the Boolean function like this. Okay. So you have to, we'll have this. And now, when will you stop? You will say that until my fj plus 1 and fj, they become the same, right? Now, there is one thing you note here that syntactically the two functions may be different. We are talking about the equivalence of the two functions. Syntactically to the two functions, because you are adding some exist, some form like this, right? Syntactically, they may be different. But you want to stop when the two functions fj plus 1 and fj, they are the same. So how do you stop? Like how do you, they are syntactically different functions. How do you even check whether they are the same function? How do you check whether they're the same function? Is the question clear?
Yes.
Right? Yeah. Syntactically, fj plus 1 may look different from fj. But I'll say that I'll stop when I reach a fixed point. That means the fj plus 1 has to be the same as fj. So essentially, it means that these two are equivalent functions.
So we'll look at the evaluation of the function on the input. Right?
Evaluation of the function, but so are you going to evaluate it on every possible values of x? Like, because x can have x is, let's say there are x has n bits. right? Like, so x1, x2. When you say you are going to look at the evaluation of x, of course, you can do that, which means that on all 2 raised to n possible values, you can check this and you can say, oh, okay, these two functions are equivalent. But is there something else you can think of based on what we have seen
Like we know
recently?
what all points satisfy fj of x. So now we can only look at things which are outside that
Uh-huh.
and check if one of those satisfy fj plus one.
Can you repeat? I did not really follow.
Like we know what all points are there in the set fj x bar.
Uh-huh.
So to check if something extra is in fj.
But how do you know which is in, like, you are given the function and how do you know like which points are there? You just know that there's a function, but
Oh, I thought we can keep a track of it at every step.
I mean, that is like then explicitly I'm keeping track of. Like if I have to keep track, then I'm explicitly keeping track of all the states, and it somehow defeats the purpose then because I'm again going back to explicitly maintaining everything, right? So that's not what we want. But we have seen something very recently. In order to check the equivalence, what can we do? Sorry? Huh?
A game?
The game.
Some game then.
No, it's not a bisimulation game. It's a Boolean function, right? We are talking about Boolean function. Boolean function. And then how do you can really talk about like these two Boolean functions are the same?
So this reduced ROBDDs and
ROPD, right? So if you see that like you have two functions, we always say that like if you have an ordering of the variables which you can fix a priori, the ROBDDs will be exactly isomorphic. They are the same ROBDDs, right? So all you can do is like at every point you maintain the ROBDD of the function and then you see that whether it has you get the same ROBDD, right? So that's where the BDD essentially helps. Now you can connect something. See, I'm also not a practitioner, so I have not used and seen, for example, like how using ROBDDs compared to an explicit model checking, how things it makes fast. But people say that it just does magic. Like I mean, it can do some trillions of states with ROBDDs. You can do model checking with so many states and all. Okay, so that's the thing. I mean, like these data structures. I mean, it's just a data structure. The ROBDD is a data structure which allows you to do this model checking of system like with number of with a state space which is several magnitude higher than what you can do with explicit state model checking. And there are different other techniques also. I'll just mention a bit at the end in the passing maybe, but like this is just one thing we saw, which is called a symbolic model checking, right? Uh, I mean, these are all different heuristics that people use in order to make things useful. Okay, so this is for just the exist eventually. A slightly more generalization of eventuality is the until operator, right? Like you can talk about exists, for example, C until B. Okay, so what is that fj here? Like I'll just write. So this was like this. Okay, so let me bring it here. And then you can tell me what is the modification that we are going to have here. Um, so we have these, but now what change should we have here? What change should we have here for the C until B? For the C until B. Instead of eventually B, we are talking about C until B. So you should satisfy, I mean, you should, of course, go to B, but when you are going to B, you should also satisfy the C at every step, right? That's what it does. So what shall I do here? I'll just say that either it is that tj plus 1x is either that tj of that tj union this thing, but in this union I should say that s belongs to not only just any S, but S belongs to SAT of C, right? That is how it should be, SAT of C. Okay, so I'll just say that here I'll have like some chi C of X bar. So SAT of C corresponds to the chi C, which is like the characteristic function. And you have the following, right? So this is the whole thing. Okay, so this does exist preemptively. Clear? Okay. So what about this? If I just say exists X B, just here we don't need a fixed point. We just talk about the next state, right? It's a simpler case. So this I'll just say the function will look like this, that there exists some X bar prime such that delta of X bar prime and chi b of X bar prime. Clear? Yes, fine. Now what about this exists GB? So it is always, right, that B. So here, what sort of fixed point we will be looking at? That is, it is the greatest fixed point because we start with the B and we remove things, right? We remove things and we are going to reach a greatest fixed point. So how do you, what should it look like?
Fj minus.
Yeah, but minus you don't usually write. Like, so you can think of this as like that if so suppose I have the like if you consider in terms of the sets Tj, let's say, right? So what does the set Tj of B or the set yeah, just the set Tj, what will it denote? So let's see here. So for example, here when I talked about the set Tj, what does the J denote? What does the index J denote? When I'm talking about eventually B, what does the index J denote?
Steps it's satisfied.
In J steps, within at most J steps, I'm going to see a B. At most J steps, right? When I'm talking about the globally here, then if I talk about the J, what should the J denote?
So from that for J steps it's satisfied.
For J steps, like I should be able to satisfy. Okay. So it's like so when I'm at like, is it exactly J steps or is it
No, at most J steps.
At least J steps should satisfy.
Yes,
at least J steps, right? I should be able to do at least J steps. Exactly. I should be able to do for at least J steps, right? So now here, so what I'm saying is like, I should be able to, so if J plus 1 is like, I should be able to do for at least J steps and maybe also for one more. I mean, in addition, can do something for one more. If J plus 1, I should be able to do, if I can do for at least J plus 1 steps, I should be able to do for at least J steps also, right? So this is then, here I had a disjunction. If you see, here I had a disjunction, correct? So now, instead of a disjunction, I'm going to have a conjunction. Clear? So I have if j of X bar and what? X bar prime. Now you tell me.
that delta X
Delta of X prime, right?
and X prime in Fj X.
Fj of X bar prime. Is it okay? Clear? Good? Good.
And X bar should satisfy B.
X bar should
satisfy me.
Yeah, that is, I'm starting from here itself, like it should, that I start from there, right? I should always be in B to start with. And then I say that in the next step, I should be either, I mean, I have to be able to satisfy B now as well as for one more step, at least for one more step. Okay. Yeah. And then when you have the Boolean connectives, like if you do this, you can have like just, for example, using this inductively, you can define the function. If you have a phi1 and negation of f phi2 and so on, right? So as I was saying that here, this is where the BDTs are, the RO BDTs can be useful, right? Yeah. So what is binary decision diagram? I mean, as just to say again, like these are the appropriate data structures. Like some data structures, I mean, it's a bit strong to say appropriate, but it's certain data structures which people have empirically found that they work really well. Okay, and make these model checking algorithms really practical for really large scale systems. Now, of course, I think somebody was suggesting you can also equate the two functions by saying truth tables you can have, like, but they are not efficient. And you can even talk about conjunctive normal form, disjunctive normal form, but again, like there can be an exponential time required to check their equivalence if you have in conjunctive and disjunctive normal forms and things like that. Now, there are certain other techniques which also people use. So this is one thing that we saw, which is the symbolic model checking, right? What we saw is symbolic model checking. Symbolic model checking is what we saw, right? Particularly in the context of CTL model checking. And this is as opposed to what the standard thing that we first learned is called the explicit state model checking, which doesn't scale well. Like for you do everything for individual states. It doesn't scale well. So that is explicit state model checking. And then we are talking about symbolic model checking. And now there can be other things, like one is other techniques, okay, to make model checking more scalable. So one is called symmetry reduction. Symmetry, what is symmetry reduction? Like essentially like we saw these bisimulations and all, right? Where there are the states which are similar to each other. There is a symmetry over these states. And you can do the quotienting. You recall like the quotienting, that merging the states which are equivalent them together. And that is like the symmetry reduction. Like if you have a large state space and many of the states are similar to each other, you can make it smaller, the structure smaller, and then do the model checking on the smaller state space, right? On the smaller system, which is equivalent in terms of the behavior. Um, then there is something called bounded model checking. So the idea is that sometimes if you suppose you have a program, in the program you want to check whether the program satisfies certain property. Now, often what happens, like there will be loops in the program, right? And it is often the case that, I mean, again, people have empirically found that when you are violating some property, it may be the case that you are violating the property not too much deep in the program. So you can just unroll your loop a finite small number of times and you are going to violate. You will get to see most of the violations with a small number of unrolling of the loop, right? So you just unroll the loop a few times and then you essentially say that, oh, this program violates this property. Now, what you lose here is completeness in the sense that, for example, there may be still some bug which require like unrolling a loop several times, but you may not be able to catch such things. But if you say that this is something that you have found a bug, then that is sound in the sense like the bug definitely exists. You have been able to find the bug, but there may be some bugs which you may miss, right? Because you put a bound on. And then there are very nice theories about something called partial order reduction, which is quite, and each of them is like a significantly big topic in itself. So we saw some of this, the symmetry reduction in terms of the bisimulation, etc. We saw. The idea of partial order reduction is like there can be several paths in a program, right? And all the different paths may lead to, like, for example, you have one path like this, you have another path like this, you have another path like this, and then they have been reaching some same state. Okay. Now there is an order across these states, but there is a partial order. You may not have a total order, but maybe the interesting points that you would like to check are here and here. You don't have to go through all the possible executions. So you only somehow find the interesting points and you say that, oh, these are similar in behavior in terms of where you at which point you are checking your property. And you just say that, well, I only need to consider one path. I don't need to consider all the paths. And then there are again lots of data structures people use in order to sort of do such things called this partial order reduction. Okay. So it's again a little, you need a lot of engineering in order to devise data structures, which data structures to maintain, what works well, and things like that. Okay, good. So I think I'll stop here today a bit early. So I'll have to let me stop the any question before I. So